Okay, good morning, everyone. Am I audible?
Good morning, sir.
Good morning, sir.
Good morning.
Good morning, sir.
Yeah, so let's go back to what we were discussing. I hope that you can see the screen. So is my screen visible?
It's loading, sir.
Okay,
Yes, sir, it is visible now.
good. So we were discussing something about the molecular aspects of how electronic transitions within a molecule are important in terms of understanding uh, the range of wavelength in which these molecules will tend to absorb. Also, how is it important in terms of predicting uh, what could be the molecular structure uh, when we know that in which range the compound is absorbing. So we will take our discussion forward from that point. And yesterday I gave you this idea that when we look at the range at which the molecule is absorbing, what kind of transitions happen in that particular range. Uh, this picture shows you that. So, do you remember at the end of the lecture, what was the question that was asked to you?
Yes, sir.
Okay, so did you try to find out the answer? Yes, anyone? So should I repeat the question once again so that it sets the tone for today's discussion?
Yes, sir.
Okay. So the question was that okay, if we see that the molecule is absorbing in this area, then we can predict okay that there are single bonds. There is nothing exceptional about the molecule. Obviously, the molecule must contain single bonds. If it is giving you some absorption in this area, then you can predict that one of the two atoms in which the bond is present, that means the single bond is present, at least one of the two atoms must have a lone pair. So that also can be predicted. But the situation was slightly different in terms to understand that if we are talking about absorption that is happening in an area which is more or less occupied, if you look at it, the absorption area here is overlapping for one particular type of transition. So if you look at this portion, almost starting from this area to this area, this is an overlapping region. That means if any molecule gives you absorption in this region, then it becomes difficult for you to predict that whether it is giving absorption only due to pi to pi star, that means only due to its existing double or triple bonds, or is it because there is an additional transition happening, that is the n to pi star transition also happening. So to give you a perspective of what I'm trying to ask is somewhat like this. If I take, say, for example, if I find out the absorption spectra of the molecule, and the absorption spectra looks like this, so I know that the molecule absorbs heavily at 520 nanometers. Okay, but 520 nanometers falls somewhere over here. So this is the range where you can get both pi to pi star as well as n to pi star transition. So now your what you can say challenge to find out is whether this 520 nanometer transition that you see is because of pi to pi star transition only, or in addition to pi to pi star, there is n to pi star transition also taking place. Is the question clear?
Yes, sir.
Okay, so if the question is clear, then you need to apply all the understanding of the transitions that we talked about in the last class, as well as you need to find out something about, or you need to remember or apply something about the character of pi electrons, and try and find out that what could be the way in which you can predict that, okay, my molecule is giving me transition due to both pi to pi star as well as n to pi star, uh, or is it only because of pi to pi star transition? So what do you, first of all, just to give you guidance towards getting to the answer, what do you remember about the character of the pi electrons? Yes? Yesterday, in the last class we discussed that what is the character that is associated with pi electrons. Which of the two electrons that are involved in bond formation, according to you, are more stable? Pi to pi star or n to pi star? Pi to pi star. Pi electrons are more stable in giving you a stable bond, or the sigma electrons are more stable in giving you stable bond formation?
Sigma electrons.
Obviously, sigma electrons are more stable. And what was the reason that we discussed in the last class? Why is it so?
Energy requirement.
Not exactly, but meaning you can correlate it like that. But yesterday I told, that means in the last class, I gave you the reasoning why we consider that the sigma electrons are more stable
Yes.
than the pi electrons. Yes? Anybody
Yes,
was?
cloud.
Yes? Sorry? I couldn't hear
Pi
you.
bonds are in the cloud of pi electrons, so they can easily delocalize and they are not stable.
Uh, so they are more localized or more delocalized according to you?
Delocalized.
Yes,
Delocalized.
they are more delocalized. That means if I show the pi electrons, then the pi electrons can be found anywhere here in this cloud area, right? So they are not exactly, you cannot predict that where will be the pi electron located. So the understanding is somewhat like, when we talk about pi electrons, they are more delocalized compared to the sigma electrons. Sigma electrons, if you remember, I told you something about the bond status, like if there is a single bond existing between two same atoms, say for example, then the sigma electrons are said to be cylindrically symmetrical. That means they are drawn like this. They are exactly in the middle of the two atoms, and hence they are shared uh, equally with the two atoms. However, if we consider the pi electrons, say in the same two atoms, they are bonded together, then the pi electron distribution is shown like this, above and below the bond. It is, this is what we have seen just now, right? In the last slide, you saw that how the structure of the pi bonding orbital was like. So the distribution of electron can be somewhere over here, anywhere over here in the pi electron cloud. So compared to the localized nature of sigma bond electrons, the pi bonded electrons are much more delocalized. They are slightly more, what you can say, more mobile compared to the sigma electrons. And that is what gives the pi electrons a kind of, what you can say, a kind of slightly flamboyant kind of nature. Okay, so can you apply this understanding of the character of pi electrons to have some reasoning in order to predict that how you can distinguish between pi to pi star transition and n to pi star transition? Is it this kind? Is this kind of understanding of the pi electron character compared with the sigma electron character in any way helpful for you to distinguish between pi to pi star transition and n to pi star transition? What, according to you, are non-bonding electrons? They are localized or delocalized? Non-bonding electrons form the lone pairs. We discussed about this also. So what, according to you, the non-bonding electrons are like character-wise? Are they similar to pi electrons, more delocalized, or they are similar to sigma electrons, more localized? The non-bonding electrons. Is the question clear?
Yes, sir.
Okay, so what, according to you, could be the character of non-bonding electrons? Yes? More localized or more delocalized?
Some may be localized.
They are more localized, right? Like very similar to sigma electrons. They are associated with one of the two atoms, and they don't leave that atom, correct? So they are more or less confined to that particular atomic orbital only. They are never going to get transferred into the molecular orbital, correct? So now, does this any way help you in making out the reasoning that how can you distinguish between pi to pi star kind of transition and n to pi star kind of transition? Okay, what, according to you, will be more favored? More favored kind of a transition, pi to pi star or n to pi star?
Pi to pi star.
Okay, why do you say so?
As they're more delocalized,
So,
so according to their energy requirement, they can easily मतलब transition state में जा सकते हैं, उनका transition होके excited state में जा सकते हैं.
so non-bonding electrons, you believe, cannot undergo that kind of transition. It is not a favored transition. But it is energy-wise, meaning favored transition is having anything association with energy value, or it doesn't have any association with energy value. When you say easy, what do you mean by easy? Less energy or more energy? Or doesn't have any relation with energy? Yes? Okay, I'm giving you an analogy. Okay, perhaps that will help you. Okay, just imagine this situation that you're at your home and somebody rings your doorbell. Okay, you open the door and you find a person who is very dear to you. That means you know the person. Will you offer him to come inside the home, or that means will you take him inside, or will you not?
We will.
You will. Okay, fine. Now imagine another situation. You are at home and a doorbell rings, and there is a completely unknown person standing in front of you. Okay. Will you offer him to come inside or will you not?
No, sir.
You will not. Okay. So this was an analogy. Okay. So analogy is something like a known person. Now see, pi to pi star transition. Now when we talk about the pi star orbital, it is developed or it is created from, meaning has a structure which is quite similar to the pi orbital as well, right? Just look at the previous slide. If you take a look at it, antibonding pi star orbitals and bonding pi orbitals, they are created from the same source of energy, right? However, when you talk about non-bonding electrons, now these non-bonding electrons can be present anywhere in any orientation, right? Now, why I'm telling you this is because we know that the pi bonds are formed due to lateral overlap, right? So if I draw like this, then one orbital, atomic orbital was like this, another atomic orbital was like this, and then there was a lateral overlap happening, correct? And hence you were getting, but both these orbitals, that means the electrons which were residing in both these orbitals were oriented along the same plane, right? Consider this as a y plane. So both these electrons were in the y plane. So automatically, when you create a bonding pi orbital, it will be in y plane. And anti-bonding molecular orbital will also be in a y plane. Does that make sense?
Yes, sir.
Okay. Now, for non-bonding electrons, these non-bonding electrons can be present in any orbital, correct? So imagine that they are present in the z orbital. Just for understanding, they are present in z orbital. The electrons are in the z orbital. So do you believe that when the electron gets excited from the z orbital, it might land up into a pi star antibonding orbital which is oriented along y-axis? The analogy could be somewhat like you are changing the plane of the electron after it is getting excited. Is it not happening so?
Yes, sir.
Right? Meaning you are not going to jump from one plane to the next plane in the same, what you can say, on the same axis. Rather, you will be jumping into another plane which is in oriented in completely different axis, right? It is not in the same axis at all. So what will be favored according to you? A pi electron in pi star or a non-bonding electron in pi star?
Pi to pi star.
Correct. Pi to pi star will be more favored. Now, when I say it is more favored, then it doesn't mean that it requires less energy, because the energy value will be same. Energy confined to 520 nanometer will be same for both the transitions. But the magnitude of the transition, now what do you mean by magnitude, is that the chance of the transition, meaning non-bonding electron takes the same amount of energy, tries to jump, but it cannot stabilize because it cannot find the same, what you can say, plane, higher energy orbital. So it might fall down. But sometimes there is a chance by the way of which it finds in another plane the excited state orbital. Does that make sense?
Yes,
So
sir.
the chance of pi to pi star transition, that means the chance that when the pi electron accepts this amount of energy, it will stabilize in pi star orbital is more compared to the chance when the non-bonding electron jumps and lands up into the pi star orbital. Okay. So when we talk about the peak height for n to pi star, the peak height for n to pi star will be this, while the peak height for the pi to pi star will be this, right? So this was a kind of what you can say analogy to let you know that the extent of absorption due to N to pi star transition will be only this much at 520 nanometer. But the extent of absorption due to pi to pi star transition will be this much. So when you see a peak, you actually see a combined peak. Are you getting the point? So if both the transitions are happening within a molecule, you will see a combination of the two peaks appearing over here. So the peak height, this is because of absorption due to both N to pi star as well as pi to pi star clubbed up together. So you see the peak height like this. So in order to find out, now the problem is, what's the problem now? If you know this much portion, what's the next problem?
How to distinguish?
Yes, how to distinguish, right? Because we are seeing only one peak. We don't know that whether that peak is due to pi to pi star or N to pi star or is a combination peak. Are you getting the point? Right?
Yes, sir.
Okay. So now how will you find out that whether N to pi star transition is actually happening? Pi to pi star is happening for sure because the region is confined for pi to pi star. And also N to pi star can happen when pi star is available. So obviously we know that pi to pi star is happening for sure. So the molecule has to have double or triple bonds. But we don't know whether the molecule has lone pairs also or not, right? So our actual aim is to just find out whether there are non-bonding electrons also responding in the same manner or not, right? So by some or the other way, if I can resolve these two peaks, that means if I can separate these two peaks from each other, then my job is done, correct? Meaning, by chance, if I get an N to pi star peak shifted in the wavelength axis and pi to pi star peak shifted, then perhaps I can resolve the two peaks from each other, right? But it's a difficult thing to do. So by any chance, are you getting to any answer now? Now we need to consider all of these factors. Okay, one, we need to consider the character of the pi electrons compared to the character of the non-bonding electrons. We also need to know this, that N to pi star transition is going to give you a small peak compared to pi star transition. Okay, but now the major challenge is to segregate these two transitions. And how will you do it? Is okay, I'm giving you the answer now. Okay, imagine now the situation is like this. Okay, uh, you are a quite an outgoing person. You like to have fun. You most of them like to have fun. Okay, and the situation is like this, that you have your exams scheduled the next day. Okay, now say suppose I offer you a free cinema ticket today. How many of you will take it? The exam, you have an exam tomorrow, scheduled tomorrow, and now I'm offering you a free cinema ticket. How many of you will take it?
Very few.
Very few, right? Okay. But very few will be there, meaning they will be somewhat like outgoing types, and they will forget about their exams and they will try to get the free cinema ticket and go to the movie. Correct? In
Yes,
such
sir.
situations, what the consideration point is, offering a cinema ticket is a kind of what you can say, uh, I'm kind of offering you what you can say, not getting the exact word, uh, एक लालच है तुम्हारे लिए, right? So those who can fall to that lalach will take up that ticket, correct? While those who know, those who are serious enough that, okay, I need to go for my examination and I am not completely prepared. So forget about the cinema. I can buy the cinema ticket anytime. Forget about the free cinema ticket as well. I should study, right? But if I say that the thing is like I am offering you a free cinema ticket, but the examination is now getting rescheduled after 4 days, how many of you will take it?
Almost
Most of them,
more
right?
than 50%. Yes.
Yes, more. Still, there will be some people who will be still conserving themselves. Okay, no matter what's the situation, I am going to face exam in 4 days, and I need to study well. Correct. There will be few of them who would be always there, shielding themselves from those all sorts of what you can say lalach, right? But there will be many of them who would be falling for the cinema ticket. Now, what I am trying to convey here is that imagine that those who are falling for the cinema ticket are those similar to the pi electrons. They are available to have that kind of an interaction, right? They are available to fall for that situation where you are getting a free cinema ticket or a free voucher or something like that, right? However, the non-bonding electrons are those type of people who, no matter what is happening, they are more focused towards examination. So they will not fall for any such what you can say pleasures which are given to you. Okay. So when we compare the number of available people compared with the number of unavailable people, the number of unavailable people will be very less compared to the number of available people. Most of the people will fall for this kind of a situation, right? So when you are falling for such kind of a situation in terms that you are given an atmosphere by the way of which uh, you you are forced to take up a decision that you will go for watching a cinema, then this force can be created somehow. Now the energy values for transition are more or less same. This is just an analogy given, okay? But the energy for the transition is more or less same because we are looking at only 520 nanometer energy value. Here, the situation is I can give them some kind of another responsibility. That means another environment. Okay, and what that kind of environment be? That environment is more interacting kind of environment. Now, why people want to go to cinema or want to go to some other party places? The reason is that they can interact with several people. They want to get mixed up with several people. However, why can't a few of them are more focused and don't want to go to such places? Because they are not available for that kind of an interaction, in the sense that they don't like that kind of an interaction. So can we not say this, that the non-bonding electrons are not actually being going to be more interactive compared to uh, the pi electrons? So can we say that the pi electrons are more interacting compared to the non-bonding electrons?
Yes, sir.
Yes. Okay, and that is why pi bonds are unstable, in the sense that the electrons are not very stable. Okay, they can interact with the surrounding environment, and which is an interacting environment for these electrons. The interacting environment for these electrons are the polar solvents. Now, I hope that you know what are polar solvents. Yes, heard about this term previously, polar solvents?
Yes, sir.
Okay, what are these? Okay, what is polarity according to you? Okay, as I'm not getting any answer. Polar solvents are those in which the molecule has two poles in it. Okay, like for example, if I consider water, water is drawn like this. Okay, and we know that in case of water, the hydrogen is delta positive. That means it's partially positively charged, while the oxygen is delta negative. That means partially negatively charged. That means what it actually means is that the electrons which are involved in bond formation are actually pulled towards oxygen because of its electronegativity. So the electrons are more localized towards oxygen and less available for hydrogen for interaction. So you get two poles within the same molecule, right? One is a negative end and the other is the positive end. Such kind of solvents are normally referred to as the polar solvent. Now this is not a charge, okay? So let me give you another example. This is that means polar nature is not always associated with charge. Like we say North Pole and South Pole, right? Yes. So we say North Pole, we say South Pole for a magnet or for Earth, you can consider. The reason we are saying poles is because they have two dissimilar characters. I can also talk about a pencil or a pen. Okay. If I draw a pencil or a pen like this, then one end of the pen is from where you can write, while the other end you cannot write from that end. So I can talk it like this is the head, this is the head and this is the tail, or this is the head and this is the tail of the pencil. So you have two dissimilar ends. When you have to any molecule two dissimilar ends, no matter whether it is with respect to the charge status, whether it respect to the groups which are oriented in the molecule, whatever it may be, is not necessarily associated with charge. But if it has two dissimilar ends, then you cannot convert this end to write something. You have to write from this end only, correct? So automatically this becomes a polar system. Two different poles the molecule has. Is it clear to understand?
Yes, sir.
Right. So when we say polar solvent, consider water molecule. It is interacting solvent or non-interacting solvent according to you. What gets dissolved in water easily?
Interacting molecules which can form hydrogen bonds
Yes.
with water.
I can consider it like this, that anything that can break the existing bonds between water molecules themselves can get dissolved into water. Can I say this? Okay, I
Yes.
will put it again. Like in water molecule, you get a structure which looks somewhat like this. It is somewhat like a lattice structure. This is called as a lattice theory as well. It is believed that all water molecules are oriented like this because this is delta positive and oxygen is delta negative. So there exists a kind of a weak interaction between these hydrogens and these oxygens. Likewise, you can imagine that how the structure might be formed. So anything that can break this and can form a better bonding can get into water. Obviously, if it can form a better bonding, then it must interact with water, right? Point is clear?
Yes, sir.
So which of these two electrons you believe will be available for this interaction? Non-bonding electrons or pi electrons? So polar solvents are interacting solvents. They like those people who are available for interaction. And which, according to our analogy, which of these two are available for interaction? Non-bonding electrons are available or the pi electrons are available for interaction?
Pi electrons.
Yes, pi electrons are available for interaction. Now, in such a situation, when you allow a molecule which is preferentially undergoing pi to pi star transition, its pi electrons, when they are getting a polar environment, how they are going to behave according to you? Are they going to interact with the solvent or they are not going to interact with the solvent? Yes.
Interact with solvent.
Yes, they will interact with the solvent. Now, when this interaction begins, now see, there was pi to pi star transition happening. Now you are putting up such a molecule into an interacting solvent. So pi electrons start to interact. Interaction of pi electrons actually change their original position with respect to their to the environment. Now what happens is somewhat like this. Okay, interacting people will come to know that okay, there are free tickets available, right? However, if the people don't want to interact, will they come to know ever that there are free tickets available?
No.
Yes. So now if there are free tickets available for interacting people, then will they not be more excited than what they were previously?
Yes, sir.
More excited means they are already slightly energized, and now they need lesser amount of energy for transition. Imagine this, that previously they were placed here. Now, as soon as I give them the ticket, that means as soon as I put them into polar solvent, because of their interaction with the polar solvent, their energy is slightly already elevated. That means they are slightly more excited now. Okay. And if they are already slightly more excited in the polar solvent, their transition will happen even more easily, right? They will require less energy to undergo the transition. So now when we are talking about pi to pi star transition happening in the polar solvent, there is a shift. Previously, they were absorbing at 520 nanometers, and now suddenly, because they are in polar environment, the energy for transition becomes slightly less. And now, if we compare the same situation of putting up non-interacting electrons, that are non-bonding electrons, in polar solvent, what will happen to those electrons according to you? Now imagine this situation, that some of your friends falls into a category of pi electrons, that means interacting electrons, while you fall into the category of non-bonding electrons, that are you don't like interaction. Okay. Now pi electron, which is your friend, continuously starts giving you messages on your WhatsApp that I have free ticket, let's go for a movie. I have a free ticket, let's go for a movie. But you don't want to go for the movie because you want to study for the examination. You are non-bonding electron. What you will do? Yes, he's your close friend, continuously sending you messages on WhatsApp that I have free ticket, let's go for a movie. And you belong to a category of non-bonding electrons. So what you will do? You don't want to go to the movie, you don't want action to happen. What you will do? The environment is now becoming polar for you, right? The environment is interacting, but you don't want to interact. What you will do? Yes? Will you not shut down your mobile so that you're free from any kind of distractions and you can focus on your studies? Yes? What you will do according to you if you are put up in such kind of a situation? Your friend is an interacting person who likes to be in the polar solvent. He got the free movie ticket. Now he's continuously telling you, that means he's giving you the polar environment kind of an environment, and he's continuously sending you WhatsApp messages that let's go for a movie. I'm having a free ticket. What you will do? You are non-bonding electrons. Don't want to interact with anybody. because you want to focus on examination. What's your take? What you will do?
So
You
I
will try to, yes, yes,
either
Pooja,
will
go
not
ahead.
contact with that friend, or after some time
Okay.
we may reconsider the decision and go for that.
No, movie is destined for a particular time, right? There is a show at 12 o'clock and your friend is pinging you continuously at 11 o'clock. Will you prefer to see that ping, or will you prefer to switch the mobile, turn off the mobile?
Yes, turn off the mobile.
Right. So what you are actually doing is that when you are turning off the mobile, then you are actually trying to become more stabilized. You want to focus more on the exams, right? On your studies. So you will slightly drop your energy. So what the non-bonding electrons do when they are in the polar solvent is that because they don't want to interact, they want to remain with the atom in which they are already there. So they will slightly lower down their energy. Now the transaction becomes slightly higher energy transaction. Are you getting the point? So now what happens for pi to pi star transition when it is in polar solvent? The energy of the transition slightly gets reduced, while the energy of n to pi star transition in the polar solvent increases because non-bonding electrons slightly drop their energy. They are trying to become more stabilized. So there is a shift again in the pi n to pi star transition. Are you fine? Is the session clear enough?
Yes, sir.
Yes. Okay. So now you distinguish between n to pi star, pi to pi star to so how will you distinguish between pi to pi star and n to pi star transition?
On the basis of their absorbance and the peak we get.
Yes, on the basis of their on the basis of absorbance, no doubt. But you will solubilize the molecule into polar solvent and look at the shift. Where is the shift happening? Now, previously it was at 520. Now, after you have solubilized it into polar solvent, if the peak shifts towards say 540 nanometers, what's your conclusion? What are the transitions you are looking at?
Pi to pi star.
Yes. So you know that your molecule has only pi to pi star transitions now. However, in addition to 540 absorption, you also get an absorption at 510. What's your conclusion? That means you get a peak at 540 as well as you get a small peak at 510. Your conclusion would be that your
It will
molecule has
both.
both the transitions going,
Yes.
n to pi star as well as pi to pi star transition. Okay. So by changing the polarity of the solvent, by changing the solvent conditions, you can actually find out that whether the transitions happening within your molecule are pi to pi star, or in addition to pi to pi star, there is an n to pi star transition also going on within your molecule. Now, this becomes important because you can now tell conclusively that whether your molecule has only pi electrons or in addition to pi electrons, it also has non-bonding electrons. So the bond within your molecule, whether it is only double bonds or whether there are, in addition to double bonds, there are certain atoms with lone pairs also. So can you not distinguish this?
Yes, sir.
So these kind of studies in which you solubilize your molecule into other solvents and try to distinguish what kind of transitions are happening within your molecule, such kind of studies are called as solvent perturbation studies. Okay. And this will come into picture more when we talk about the applications of UV visible spectrometry. Okay, and we'll slowly go into the application section because we don't have much of a time in order to put up for applications and all stuff. Okay, so but we cannot actually start it up today itself. Okay, let me put it another situation. What will happen if you are putting up the same molecule now into non-polar solvent? What will happen to pi to pi star transition according to you and n to pi star transition? Non-polar solvents are not interacting solvents, which don't want to interact with the solute. So for example, the situation is somewhat like non-polar solvent. I can give you an example of petroleum ether. So in such situations, only non-interacting solutes can get dissolved. So in such solvents, only non-interacting solutes get dissolved. So the understanding is that interacting solutes or polar solutes can go into polar solvents, and non-interacting or non-polar solutes can get dissolved into non-polar solvents. Okay, so now imagine this situation that you have put up your molecule into non-polar solvent. What will happen to pi star transition? Yes. So it is something like those people who like to what you can say, who like to go out, play, and mix up with people. You are making them sit in a particular classroom, attend a particular class. Is somewhat like that.
Maybe they will drop their energy now in this case.
Yes. So their energy would be less now because they don't like this environment in which they are. And now the transition becomes difficult for them. So the energy for the transition will be more. So where this pi to pi star will shift towards shorter wavelength,
Left,
higher energy
yes.
value, right? Okay. And what will happen to n to pi star, by the way?
Maybe there will be no shift.
Yes, there is no shift. Nothing will happen to n to pi star. They are in the environment where they want to be in. Okay. So no kind of shift will happen. Okay. So I hope that I have given you sufficient amount of detail in how you can distinguish between the type of transitions which are happening within the molecule just by dissolving the molecule into a polar solvent or in a non-polar solvent, right? So when it is in non-polar solvent, pi to pi star will shift towards shorter wavelength, n to pi star will remain at 520, while uh, when it is in polar solvent, pi to pi star will shift towards longer wavelength and n to pi star will shift towards the shorter wavelength. Is this much fine?
Yes, sir.
Yes, sir.
Okay. Are there any questions that are coming up in your mind regarding this understanding? Yes? No questions? If you are not getting any questions, I have one question. If you are getting this kind of shift in the polar solvent and in the non-polar solvent, in what situation you are going to get or see this peak at 520 nanometers? Did you get the question? Did you get the question or should I repeat it?
Got it, sir.
Is it not valid? Okay, is it not valid to ask? See, if you want to take absorbance, most of the times you will dissolve your sample into some solvent, right? So you'll either see already shifted peaks, correct? You'll see already shifted peaks, correct? So if your molecule is already into the polar solvent, you will already see the shifted peaks. How will you find out that the original peak was at 520? Is the question clear now?
Yes, sir.
If you shift it from non-polar solvent to polar solvent, then due to pi star, you will see a big shift, because in non-polar solvent, pi star will be somewhere below 520, while in polar solvent, pi star is much above 520, right? So there you can see a big shift. But where, in what situation are you going to get 520 peak? Is it not valid to ask?
Yes, sir.
Right? So can you answer? Okay, I will not trouble you more. The answer is that when you are seeing this peak is normally seen in the vapor state or in the gas spectra. This is also called as a gas spectra. When your molecule is in the vapor state and you are taking the absorbance, then there is no question that there is any polar environment or non-polar environment. Your molecule is all by itself. Are you getting my point?
So can you repeat it?
It is like when your molecule is in the vapor state. Imagine that your molecule is in the vapor state when you're checking the absorption. Then you will see this peak at 520. However, if you dissolve your molecule into polar solvent, you will see a peak over here. If you dissolve your same molecule in non-polar solvent, you will see a peak over here. Is it clear?
Yes, sir.
However, if your molecule is in vapor state and you're recording its absorbance, then you will see the peak at 520 nanometers. So such spectra are called as gas spectra or vapor spectra. This is normally not done with biomolecules, but just for your information, you should know about this. Okay. So I believe that this is enough for you today. In case you are having any questions regarding today's discussion, then I am ready to answer, or else we will